A buoy in the North Atlantic sent back a number this spring that made the people watching it check their instruments twice. The surface of the ocean off the coast of Ireland was warmer than it had ever been recorded for that month. And this was supposed to be a cooling year. Let me explain why that sentence contradicts itself. For most of 2023 and 2024, the planet ran a fever, driven partly by El Niño, a warm phase in the Pacific that reliably nudges global temperatures up. By 2026, that pattern had flipped. We slid into La Niña, the cool sister, the phase that usually pulls a little heat back out of the system. So the thermometers were supposed to ease off. Instead, the North Atlantic kept climbing, months ahead of where the calendar says it should be. The ocean didn't get the memo. If you want to keep following stories like this one, the strange readings, the moments where the data breaks its own rules, subscribe and leave a like. And tell me in the comments what city you're watching from and what time it is there right now. I read them. So let's start with what is actually happening to the world's weather in the middle of 2026, because the picture is stranger than any single storm on the news. Think of the global weather system as one enormous engine. Its fuel is heat, and most of that heat is stored not in the air, but in the ocean. Water holds heat far better than air does. The top few meters of the sea store more energy than the entire atmosphere above it. So when we ask what the weather is doing, the honest answer is, watch the ocean, because the ocean is where the decisions get made. The ocean in 2026 is doing something the people who study it did not expect this soon. Global sea surface temperature spent much of 2023 through 2025 sitting at record highs day after day for so long that the records stopped being news. The expectation was simple. Once El Niño faded and La Niña took over, that heat would subside. La Niña arrived. The heat mostly didn't leave. The mechanism behind that comes down to where the energy goes. When you pour energy into a system for decades, some of it goes into raising the temperature you can measure right away. But a lot of it goes into a deeper account. The deep ocean, hundreds of meters down, which warms slowly and gives its heat back slowly. That deep reservoir has been filling for a very long time. El Niño and La Niña shuffle the warm water around near the surface, but they don't empty the account. So even in a year that should feel cooler, the baseline underneath everything is higher than it was, and it stays high. That's the state of the engine right now. Fueled, running hot, and not idling the way the seasonal forecast said it would. The clearest place to read this, in numbers, is the water in the North Atlantic. The North Atlantic has been behaving like a patient with a temperature that won't come down. Through 2023, the whole basin lit up in the maps. Not one hot spot, but the entire ocean between Europe and North America, warm from the surface down, warm for months at a stretch. That event was so far outside the previous range that the scientists tracking it described the readings as several standard deviations from normal, which is a careful way of saying, this should almost never happen. And it happened anyway. It didn't happen once. It came back. What's unfolding now are marine heat waves, prolonged stretches where a patch of ocean runs far above its seasonal average, stacking on top of one another. One, starting before the last, has faded. The water off Western Europe, around the British Isles, in the Mediterranean, kept reaching temperatures in spring that it normally wouldn't reach until high summer. The calendar says May, the water says July. Picture the sea as a body of water with a memory. A hot summer doesn't just warm the surface and vanish in autumn. Some of that warmth sinks and lingers through the winter. So the next spring starts from a higher floor. Do that a few years running, and the floor keeps rising. That's part of why the anomaly runs months ahead of the calendar. The ocean never fully cooled back down between events. The consequences are not abstract, and they're not decades away. They're visible now. Warm water holds less dissolved oxygen and less nutrient, so the plankton that everything else eats thins out. Fish that live within a narrow temperature band do the only thing they can. They move, chasing the cold, shifting north and deeper. Fisheries that stood in the same waters for generations are finding their catch has quietly relocated to someone else's coastline. Marine heat waves have already been linked to mass die-offs of shellfish and seabirds, and to shifts that pull fleets across national boundaries into disputes over who owns a stock that used to sit still. But the consequence that reaches the most people has to do with storms. Because a warm ocean isn't just a problem for fish, it's a loaded weapon pointed at every coastline downwind. To understand why, you have to follow a single drop of water from the sea surface up into the sky. The chain runs link by link, and this is where the whole thing turns from a temperature reading into a wind that tears roofs off. Start at the surface of a warm ocean. Heat drives evaporation. Water leaves the sea and becomes vapor in the air. The warmer the water, the more it evaporates, and the relationship is not gentle. Warm air can hold dramatically more water vapor than cool air. For every degree the air warms, it can carry roughly 7% more moisture. So a fraction of a degree at the surface doesn't add a fraction more fuel. It adds a surprising amount. Watch what that vapor does next. When water evaporates, it carries energy with it. The energy it took to turn liquid into gas. That energy is hidden, riding along invisibly in the vapor. Scientists call it latent heat. And the word latent means exactly that: hidden, waiting. It doesn't warm the air while it's still vapor. It waits. Then the vapor rises, and high up where the air is cold, it condenses back into cloud and rain. And the moment it condenses, it releases all that hidden energy, dumps it straight into the surrounding air as raw heat. That heat makes the air rise faster. Rising air pulls in more air beneath it from the sides. That inflow starts to spin. And a storm is, at its heart, an engine that converts the hidden heat of ocean water into wind. Follow the logic back down the chain. A warmer ocean means more evaporation, which means more vapor, which means more hidden heat waiting to be released, which means a higher ceiling on how much energy the storm can pump into wind. This is why that fraction of a degree matters so much. It isn't warming the wind directly. It's raising the maximum, the strongest the storm is physically allowed to become before it runs out of fuel. And here is the part that unsettles anyone forecasting these things. A storm doesn't have to reach its maximum. Most don't. But a hotter ocean lifts the ceiling for all of them. So the rare storm that does climb toward its limit now has a higher limit to climb toward. You're not shifting the average by much. You're extending the extreme. And the extreme is the one that kills. Which brings us to the behavior that has caught forecasts off guard again and again in the last few years. Storms that don't build slowly, but jump. The term is rapid intensification, and it has a strict definition. A storm's maximum winds increasing by at least 35 miles an hour within 24 hours. That's the threshold. In practice, the storms that frighten people blow straight through it, gaining not 35, but 60, 70, 90 miles an hour of wind speed in a single day, leaping across 2 or 3 categories while people sleep. Go to sleep with a manageable storm offshore. Wake up to a monster at the door. That gap between forecast and reality is the operational nightmare, because evacuation orders take a day to carry out, and a storm can now transform faster than a coastline can empty. We've watched it happen repeatedly. Hurricane Otis in 2023 exploded from a modest system into a top-category storm in hours before it hit Acapulco, and the forecasts never caught it in time. Hurricane Milton in the Gulf of Mexico did something similar, spinning up over water that was running feverishly warm. Storm after storm has done this, and the common thread underneath them is the same. Unusually warm water reaching unusually deep, so that when the storm churns the sea, it doesn't pull up cool water to choke itself. It pulls up more warm water and feeds harder. Why do the forecasts keep getting caught? Because the models are good at predicting a storm's track, where it will go, and much weaker at predicting its intensity, how strong it will get. Intensity depends on small-scale processes inside the storm's core, physics that plays out over kilometers and minutes, finer than the models can fully resolve. So the cone on the map may be right about the path, and badly wrong about the punch. And rapid intensification is exactly the case where being wrong is most dangerous. Now here is the fact that should reorganize everything you've just heard. The scale we all use to describe hurricanes, categories 1 through 5, was built in the early 1970s. Category 5 was defined as winds of around 157 miles an hour and up. And that top step was left open-ended on a simple assumption: that storms strong enough to blow far past it were rare enough not to need their own rung. The ceiling was set by the world as it was then. That assumption has broken. Storms have already reached sustained winds well beyond 200 miles an hour. Winds so far above the Category 5 floor that lumping them in with a storm at 160 tells you almost nothing. A storm at 215 miles an hour isn't in the same conversation as one at 160, yet the scale calls them both the same thing. So, in 2024, researchers published a proposal in a peer-reviewed journal. Add a Category 6 for the storms the original designers never planned for. The idea is contested. Some argue that once a storm is Category 5, the message to evacuate is already maximal, and a new number adds nothing. But the fact that scientists are seriously debating whether the strongest scale we have needs a new top step tells you something plain. The ruler we've trusted for 50 years was calibrated to a ceiling that the ocean has quietly lifted out from under it. And once you know that a scale can be outrun by the world it was built to measure, you have to ask a harder question. What else did we calibrate to a planet that no longer exists? Start with the ceiling. If the wind scale can't hold the new storms, the next thing to check is the machine that steers them. The river of wind that decides which weather sits over your head and for how long. And that river has been telling us, through its own motion, that it's no longer running the way the textbooks describe. It's called the jet stream. Not one thing, but a family of them. The one that matters most here is the polar jet, a band of fast wind circling the planet a few miles up, near the top of where airliners fly. It exists because of a simple contrast. Cold air over the pole, warm air toward the equator, and a sharp boundary between them. Air rushes along that boundary, and the sharper the contrast, the faster it rushes. Speeds inside the core can pass 200 miles an hour. And this is where the Arctic changes everything. The Arctic is warming faster than any other region on Earth, several times faster than the global average. Follow what that does to the contrast. If the pole warms much faster than the tropics, the difference between them shrinks. And the jet's speed comes from that difference. Weaken the difference, and you weaken the jet. A weaker jet doesn't just slow down, it changes shape. Picture a fast, straight river cutting a clean channel, and then picture the same river slowed to a crawl. It starts to meander, swinging in wide loops across the land. The slowed jet does exactly that. Instead of circling the pole in a tight ring, it buckles into deep waves, plunging far south in some places and bulging far north in others. And those waves move slowly. Sometimes they barely move at all. That last detail is the whole problem, and it deserves its own second look, because a stuck jet stream is where a bad day becomes a catastrophe. Weather that moves through is survivable. A hot afternoon, a day of rain, then it passes. What breaks a region is weather that stops. When the jet buckles into a deep wave and freezes in place, the pattern underneath it freezes too. Scientists call this a blocking pattern, a stuck ridge or a stuck trough that refuses to budge for days or weeks. Take the stuck ridge, a high-pressure dome bulging north with clear skies and sinking, compressing air underneath. Sinking air warms. Clear skies let the sun hammer the ground day after day, and with no clouds and no fresh air moving in, each day builds on the last. The ground dries out, and once it's dry, there's no moisture to evaporate and soak up heat, so the temperature climbs even faster. That's how you get a heat dome, a region turned into an oven, sealed shut, for weeks. The European heat of recent summers, the extraordinary Pacific Northwest heat of 2021 that pushed a town in Canada to nearly 121 degrees Fahrenheit before it burned to the ground the next day, those were blocking ridges, jet stream waves that stopped moving. Now flip it. The stuck trough, a deep dip where cool, wet air pools and storm after storm rolls into the same spot with nowhere to go. That's the mechanism behind the floods that don't quit. Rain that would normally pass in a day, falling for a week, because the system that carries it away has stalled. The catastrophic flooding in Pakistan, in Germany's Ahr Valley, in Libya. Different places, same underlying failure. The conveyor stopped, and the weather it should have carried off just kept pouring into one address. So both of the jet's jobs are faltering at once. As the fence, it sags, letting Arctic cold spill unusually far south in winter, which is why brutal cold snaps still happen in a warming world and confuse everyone. As the conveyor, it stalls, letting heat and rain pile up in one place until the place breaks. Same weakened river, two failures. On the other side of the planet, the ocean is writing the same story in a different alphabet. In the Western Pacific, we don't say hurricane, we say typhoon. Same engine, different name for the same ocean's worth of stored heat. And the Western Pacific holds the largest reservoir of warm surface water on Earth, a region called the warm pool. That pool has been expanding and deepening. Deepening is the word to hold on to. A storm passing over the sea churns it, dredging up water from below. If the warm layer is thin, the storm pulls up cool water and starves. If the warm layer is deep, there's no cool water to reach. The storm churns and finds only more fuel. That's why the fastest intensifying storms in recent years have concentrated over waters where the heat runs deep. And it's not only the Western Pacific. The Bay of Bengal, a shallow, funnel-shaped sea that concentrates storm surge like a hand cupping water, has been producing cyclones that spin up with frightening speed and, crucially, arrive wetter. A warmer storm over warmer water carries more vapor, and it dumps that vapor as rain on landfall. So the story of these storms isn't only the wind now, it's the water they carry inland and drop all at once on cities that were built for a milder ocean. And there is a limit here that has nothing to do with wind or flooding. A limit written into the human body itself. This is where the physics gets personal. Your body runs at a fixed inner temperature, and it holds that temperature mainly one way: by sweating. Sweat evaporates off your skin, and evaporation carries heat away, the same hidden heat mechanism that powers a hurricane, running in reverse to cool you. But evaporation only works if the air can accept more moisture. If the air is already saturated, soaked with humidity, your sweat can't evaporate. It just sits on your skin. And then you have no way left to shed heat, no matter how much water you drink, or how still you sit. Scientists measure this with a wet bulb temperature. Literally a thermometer with a wet cloth over the bulb, cooled by evaporation exactly the way your skin is. It reads the combination of heat and humidity together, the number that actually matters to a living body. For a long time, the assumed hard ceiling for human survival was a wet bulb temperature of around 95 degrees Fahrenheit. Above that, a healthy person in the shade with unlimited water still cannot cool down. And after a few hours, the core temperature climbs to a place the body cannot come back from. The killer hides in plain sight. The dry number on the weather app, the air temperature everyone quotes, can look survivable, 100 degrees, and still be lethal if the humidity is high enough. Because the dry thermometer doesn't know your sweat has stopped working. The killer isn't the heat alone. It's the heat wedded to moisture. And that pairing is exactly what a warmer ocean pumps into the air over coastal cities. And the wall has been touched. Weather stations in the Persian Gulf and along the coast of Pakistan and India have recorded brief crossings of that wet bulb threshold in recent years. Short bursts, localized, but real, measured, above the line that was supposed to be the outer edge of what a human can endure. When the station data was pulled apart, these crossings turned up decades sooner than the climate models had projected. The models said end of the century. The instruments said, already here, in short flashes, in the hottest, wettest corners of the world. So here is where the whole analysis you've been following starts to look incomplete. Because every piece of it assumed the systems fail one at a time. The jet stream stalls, or the ocean overheats, or the wet bulb wall gets touched. Handle each in turn. But in 2024 and 2025, the observations stopped cooperating with that neat picture. Sea surface temperatures didn't just stay high after El Niño ended. They held at record levels through the La Niña that should have pulled them down. And the global energy balance came in lopsided. The planet had been absorbing heat faster than the models predicted, roughly double the rate expected over the previous 2 decades. Something changed in how much sunlight the Earth is reflecting back to space, and the leading suspect is a shift in cloud cover that no model had forecast. The account isn't just full, it's filling faster than anyone budgeted for reasons still being argued over. And when you feed a faster-filling reservoir of heat into a jet stream that's already stalling, and an ocean current whose job is to carry that heat away, the question stops being which system fails first. It becomes, what happens when the current itself, the one great conveyor that moves tropical warmth toward the pole, begins to slow? Follow the water north. Warm surface water from the tropics drifts up along the eastern coast of North America and across toward Europe. And as it goes, it gives up its heat to the air above it. That heat, handed off to the wind, is a large part of why northwestern Europe is far milder than its latitude has any right to be. London sits farther north in the Canadian province of Labrador. Yet London has gardens, and Labrador has permafrost. The difference is that current, carrying tropical warmth to a doorstep it would otherwise never reach. But watch what happens to the water once it has surrendered its heat. It's cold now, up near Greenland and the northern edge of the Atlantic, and it's salty, because as some of it froze into sea ice over the ages, the salt was left behind in what stayed liquid. Cold water is dense, Salty water is dense. Cold and salty together makes the densest water in the whole ocean. And dense water does the only thing dense water can do. It sinks. It plunges thousands of meters straight down. And it's that sinking, that great, cold, downward plunge in the north, that pulls the whole conveyor forward behind it. The current doesn't run on a motor. It runs on the sinking. The sinking is the engine. Now brake the engine. Warm the north, and two things weaken the sinking at once. Warmer water is less dense to begin with. It doesn't want to sink. And a warming Arctic melts ice, both sea ice and the vast freshwater store locked in Greenland, and that meltwater is fresh. Fresh water is lighter than salt water. Pour fresh water onto the surface of the North Atlantic, and you cap the region with a lid of buoyant, lighter water that resists sinking. Cold, salty water sinks. Fresh, warm water floats and stays. Add enough fresh water, and the plunge slows. Slow the plunge, and you slow the entire current, top to bottom, all the way back to the tropics. This loop has a name: the Atlantic Meridional Overturning Circulation, the Great Overturning of the Atlantic. People who study it usually just say, the overturning. And the measurements, from an array of instruments strung across the Atlantic that have been logging the flow continuously since 2004, show it is not as strong as it was. The reconstructions that reach further back, using indirect fingerprints in ocean sediment and temperature patterns, suggest it may now be weaker than at any point in over 1,000 years. The engine is not stopped, but it is running down. And here lives the paradox that makes people throw up their hands, because a slowing current means that in a world that is warming almost everywhere, one corner of it could get colder. Look at the geography, because the geography is the whole answer. If the conveyor that delivers tropical heat to northwestern Europe slows, then less heat arrives. The rest of the planet keeps warming. The heat keeps piling into the system, but this one region stops receiving its delivery. And you can already see the fingerprint. In the maps of ocean warming over the last century, almost the entire globe glows warmer. But there's one stubborn blue patch south of Greenland, a cold blob in a warming sea. That cold blob is exactly where the overturning gives up its heat and sinks. It's cold because the delivery is faltering. The current is signing its name in the temperature record. So this is not a warm world turning cold. Nothing about the physics reverses. It's that the map of who gets the heat is being redrawn. The planet's average keeps rising, while one address on it gets a smaller share than it used to. The climate isn't changing its mind. The coordinates of where the heat lands are shifting, and a place that spent thousands of years living above its latitude could slide back toward the latitude it actually sits at. For Europe, that would mean harsher winters landing on top of the wilder storms and stalled heat we've already been tracking. Colder cold and hotter hot, in the same region, from the same underlying disturbance. And just when you think you have the mechanisms lined up, a stalling jet, a slowing current, a warming pool of ocean, the sky in the last few years did two things nobody ordered, and they don't fit the tidy story. The first came from cleaning the air. For most of the industrial era, ships crossing the oceans burned dirty, high-sulfur fuel, and that fuel poured sulfate particles into the atmosphere over the busiest shipping lanes. Those particles do something you might not expect. They seed and brighten clouds. Sulfate gives water vapor a surface to condense onto, and clouds full of many small droplets are whiter and more reflective than clouds full of a few large ones. Brighter clouds bounce more sunlight back to space. So for a century, without anyone intending it, Ship exhaust was shading the ocean beneath the shipping lanes, holding heat away from the water. In 2020, the rules changed. New regulations slashed the sulfur allowed in marine fuel to cut the acid rain and lung damage the pollution was causing, a straightforwardly good thing for the air people breathe. But it also, quietly, pulled back the shade. Fewer sulfate particles, less cloud brightening, more sunlight reaching the sea surface. And when the shipping lanes were re-examined, they had warmed, and the clouds over them had thinned right on schedule. We spent a century accidentally dimming the sun over the oceans, and then we stopped, and the ocean felt it. The second anomaly is the stranger one, the one still without a full explanation. In 2023 and 2024, global temperature didn't just tick up, it leapt, running months at a stretch far above what the models projected, so far above that the usual suspects couldn't account for it. El Niño explained some. The fuel sulfur change explained some. Add every known factor together, and there was still a gap. A jump the models didn't see coming and can't yet fully close. The best current reading is that the planet's reflectivity fell more than expected, that the Earth is bouncing less sunlight back to space than the models assumed, and that the cause is tangled up in clouds, how they form, how they thin, how they respond to a warming surface. Which is another way of saying, the piece of the climate we understand least is the piece that just moved the most. And that is where the shape of what we know matters as much as the numbers. The models are not wrong about the direction. Every mechanism in this story points the same way, and the ocean, the jet, the current, the wet bulb wall are all doing what the physics says they should. But the speed is outrunning the arithmetic. The heat is accumulating faster than budgeted. The wet bulb wall was touched decades early. The temperature leapt beyond the forecast. And when reality repeatedly runs ahead of your best models in the same direction, it forces an uncomfortable question. It isn't whether the models are pointed right. They are. It's whether one of the numbers deep inside them, how sensitive the climate really is to the heat we've added, how the clouds will answer, how much the ocean will keep swallowing before it hands the heat back, is set too low. If the clouds thin more than assumed as the world warms, then the same fuel produces more warming than the same equations predicted. That number is still being argued over, in the open, in the journals, right now. Nobody gets to pretend it's settled. So come back with me to where this started. A buoy in the North Atlantic one spring, sending back a temperature that shouldn't have been possible in a year the whole system was supposed to be cooling. When I told you that number at the beginning, it looked like a single strange reading. An outlier, a glitch. The ocean forgetting its manners for a season. It isn't a glitch. Read it again now, with everything underneath it. That warm water off Ireland is the deep reservoir that never emptied, and the shade over the shipping lanes that we pulled away, and the overturning current running down so its cold blob can't spread as far, and the sun the thinning clouds no longer reflect. All of it surfacing in one number, on one instrument, on one morning. The buoy wasn't malfunctioning. It was reporting faithfully. A planet whose books no longer balance the way they did when we wrote the rules for reading them. And this forces a last reckoning with a phrase we use every week now. Extreme weather. We say it as though extreme means rare, the outlier, the once-in-a-century event, the storm that breaks the record and then lets us go back to normal. But every measure we followed here is built on a definition of normal, and that definition is a photograph of a climate that has already left the frame. The category scale was calibrated to a ceiling the storms have passed. The wet bulb wall was projected for a century away and got touched this decade. The current was assumed stable for the lifetime of everyone using the maps, and it's the weakest it's been in 1,000 years. The overturning, the jet, the warm pool, each was a fixed reference point, and each has quietly moved. So when a storm now intensifies faster than the forecast, or the ocean holds its heat through the cooling year, or the wet bulb thermometer flickers past the line for an hour on a coast in Pakistan, we call it extreme. But extreme is measured against a baseline, and the baseline is the one thing in this whole system that will not sit still. What we're watching isn't a run of freak events interrupting a stable world. It's the baseline itself moving, and the freak events are just the first places where the movement shows. If this is the kind of question you want to keep chasing, the readings that don't add up, the moment a number breaks its own rules, subscribe, leave a like, and I'll keep bringing them to you. Which leaves the only question worth ending on. Everything I've described is measured against what we agreed to call normal. But if the next 10 years keep doing what the last 3 did, outrunning the models, touching the walls early, breaking the ceilings we thought were safely out of reach, then the numbers we're calling extreme today become the numbers a child born now grows up thinking of as ordinary. The record year becomes the average year. The storm we're arguing about adding a new category for becomes the storm the coast simply expects. And when the baseline itself has moved that far, I don't know what we'll have left to call extreme. Maybe nothing. Maybe by then the word will just mean the weather, and we'll have to invent a new one for whatever comes next.